Okay, so good afternoon, everyone. Am I audible?
Yes, sir.
Yeah. Okay.
Good afternoon. Good
Yeah.
afternoon, sir.
Good afternoon.
Good afternoon, sir. You are audible.
Yeah. Okay. Uh, Pritam, do you have any question? You have raised your hand, I have seen.
Yes, sir. I have two questions from
Okay.
the week 11.
Mm-hmm. Yeah, you can go ahead and ask.
Okay, sir. So it is 11.4 activity.
Okay. Okay. Let me share it first. Which lecture is it?
So 11.4 activity 11.4.
Okay. Yeah. Now, so there is only one question, right?
Yes, sir.
Yeah. Following functions are differentiable or not? Yeah. What's your doubt here?
So firstly, I want to verify whether this statement is correct or not. So the statement is that if partial derivatives are continuous at a point, then the function is differentiable.
Yeah, so if all the partial derivatives are continuous, yeah, then the function is differentiable.
Okay, sir. Now, what do we mean by all partial derivatives? Is it
I mean, if it is
first partial,
of
right?
two variable, then fx and fy.
Yes, sir. So basically the first partials.
First partial, that's right.
Okay, sir. Isn't the third option? Okay, so
But you can, I mean, here we are seeing that the question is asked whether this function are differentiable or not. So can't you use I mean, the condition, the definition of differentiability here? That will be easier, right?
sir, I could not understand.
I mean, there is a definition for differentiability, right? For multivariable
Yes,
also.
sir. Yes, sir. Yes, sir.
So can't we use that one directly? So can you see my page?
Yes, sir.
Okay. So have all of you. So I am asking this for all of you. So h dot grad of f at a norm of h. Have you seen this? Well, when this limit exists and is going to zero, then the function is differentiable. Have you seen this? No.
Yes, sir, in the lecture.
Yeah. So if you also go in the solve with us section, yeah, this one. So this is the condition for differentiability which we are asking, right? So if you can check this limit and prove that this is zero, then we can say that f is differentiable at some variable a, right?
Yes, sir.
So we can use it directly, right? So what is basically this is saying? So let me write it. Yeah. So here all the functions are of two variable, right? So this a under tilde, that is a1 a2, so for two variable, and h is basically you can take as h1 and h2, right? So this is saying f of a plus h minus f of a minus h dot grad f this. What does it mean? This means, so a plus h means the vector usual addition, vector coordinate wise addition. So a1 plus h1, a2 plus h2 minus. Now what is this one? This is a1 a2 minus this is h1 h2. And what is gradient of f? So you know gradient of f at a is basically fx at a and fy at. So a1 a2, let me write it like this, and fy a1 a2. This vector is the gradient, right? So h1 h2 dot product with fx a1 a2 fy a1 a2. So this is the numerator we are talking about. So this is fa1 plus h1 a2 plus h2 minus f of a1 a2 minus h1 fx a1 a2 plus h2 fy a1. Right? This is the numerator. Is it clear to everyone? At least what I have done till now, is it clear to everyone?
Yes, sir.
Yes.
Okay. So Pritam, can you use this one now
Yes, sir.
to
So here
show
A1, A2 is 0.
0 0? Yeah, exactly.
So,
So if I go to the problem, so let's take the second one. Okay, xy by x square y square. This one. So fxy is xy by x square plus y square. While
so
xy,
this
oh,
one
sorry.
you need not show because we can prove that it is not continuous at 0, comma 0. So I will,
Okay, yeah,
yeah,
that's sure, right.
yes, sir. So can we do option 3?
Yeah, sure. Option 3 is root over. Okay, so this is under root, right? And this is 0, and it is origin. And we have to check differentiability for at 0 0, right? So a1 a2 is our 0 0. So our a vector is, so 0 comma 0. So what I will get, this is h1 h2 minus f of 0 0 means 0. So let me write it still, minus h1. Now we have to find out what these are, right? Fx as
Yes,
0
sir.
0 and Fy at 0 0.
Yes, sir.
Yeah. So what is Fx at 0 0? What is this value and what is this value? So how to find Fx 0 0?
So using the
That we
different,
have done earlier, right?
yes, sir.
Yeah, tell me how to do it. The h comma 0 is f of 0 0 by h, right? Is it okay?
Yes, sir.
Yeah. So what is this one? 0, right?
Yes,
Because
sir.
f of 0 0 is anyway 0 and f of h comma 0 is 0. So the numerator is 0. So the limit is going to be 0.
Yes, sir.
And similarly, fy 0 0 is also 0.
Yes, sir.
Okay, great. So we know what these two are. So let's go back to here. So let me write it here again. So f of h1 h2. So all these terms are 0. This is 0, this is 0, and this is 0. So in the numerator, we have only f of h1 h2. And what is this? This is correct. This is the
Yes, sir.
numerator.
Yes, sir.
And what is norm of h?
So it's
Norm of h is also this one.
yes, sir.
Okay. So we have to find this limit. Limit h1 h2 going to 0 comma 0 h1 h2 by h1 square plus h2 square divided by root over h1 square plus h2 square. So what we'll get? So h1 square plus h2 square, right?
Yes, sir.
So does this limit exist?
No, sir.
No. Why?
So if we take the straight line, y equals to ms.
So h1 equal to m into h2.
Yes, sir.
So then that will depend on h, that will be a function on m. So this limit does not really exist, right? So this function is not differentiable. Is it clear?
Yes, sir. But sir, I may have committed a mistake. But could you just
Hmm.
calculate fx of basically the first partial of x and y? Uh, Basically the first partial of y
But
is
I mean, has sir said the theorem in the lecture? That's why I was not
yes,
going
sir.
to.
You can go to the lecture
Hmm.
11.4.
Okay.
I think in the last 5 minutes he said it.
Okay. So what is the statement of the theorem? Can you?
So if the first partials are if first partials exist at a point and are continuous at that point, then we say the function is differentiable at that point.
Okay. So here we know that first partial exists at that point. That is true. But whether that is continuous or not, that is the question, right?
Yes, sir. So
Yeah.
since x and y, this function is symmetric in x and y, can you
Hmm.
just show the first partial of
So
x?
what is the fx you have calculated?
So it's a complicated expression. So it is y times, oh, 1 minute.
Hmm.
1 minute. It is y cube by x square plus y square when x y is not the origin and zero otherwise.
Okay. So this is your xy. This was your function, right?
Yes, sir.
So if we want to calculate fxy, so this is y root over x square plus y square minus, so this is xy half 1 by root over x square plus y square, and this. Is it correct?
Yes, sir.
Okay.
Sir, what is
Uh,
the after minus? What have you written?
here is 2x.
Yes,
Yeah.
sir.
So that is fine. Now this will cancel out. So y x square plus y square minus x square y x square plus y square power 3 by 2, right?
Okay, sir. I think this is where I made a mistake.
Yeah. So if we
Uh,
check this x square y will cancel out. So y cube by x square plus y square power 3 by 2, right?
yes, sir. Yes, sir.
So this limit does not exist basically,
Yes, sir.
right?
Okay, sir.
Yeah. Okay. So is this clear to everyone? What we have done, how we have to check the differentiability for a function? So anyone have any question on this? Yeah. Okay. So
Yes,
any other doubt from your
sir.
end?
So
Yeah.
here h in the numerator h del f of a till, that's by definition is it top, sir?
This
The
one is the definition of differentiability. If this is zero, then we can say the
yes,
function is differentiable at a. Okay.
yes, yes.
That is the definition. So if you go to the solve with us section, it is written there already. So this is already written there. If we go to the end of this, so if this is a function of n variable scalar function, and if we take the point A, which is a1 to an, then f is differentiable at a if this limit exists and it is basically 0. That's what we have to check for every function. Okay?
Thank you. Yes.
Yeah. Okay. So I hope it is clear, right? Whatever we have done. Yeah. Okay. So let me ask, do you have any other doubt in week 11? Because I heard that all other contents have been discussed in the earlier live session. So if you have any doubt, you can ask. Yeah.
Doubt in
Yeah, which one? Yeah.
question
Yeah,
number.
tell me. Hello.
Yeah.
Yeah.
Sir, I have doubt in that 11.1 question 2.
Okay. So let me see what that is. So this is the function is given and you have to calculate the partial derivative, right?
So this expression of tan inverse x by y. So I couldn't get this expression for with respect to x. I mean partial derivative with respect to x.
Okay. So tan inverse x by y. So suppose we consider one variable function, tan inverse x. What is the differentiation of this function? What is f dash x?
1 by 1 plus x square.
1 by 1 plus x square. Okay. Great. Now what if there is an a, some constant?
A by 1 plus x square.
A by 1 plus
X.
a square x square, right?
Yes.
Okay. Now here the function is given as tan inverse x by y. Okay.
Yes.
So f x y tan inverse x by y. Okay. So when I am differentiating with respect to x, basically I am treating this 1 by y as a constant. So 1 by y as my a, correct? So
Okay.
this is nothing but tan inverse 1 by y. This is a constant term. You can treat this as a constant and this is your function, right? So what it should be? 1 by y, 1 plus 1 by y square, x square, correct?
Yes.
So now can you simplify it? X square by y square. So this is 1 by y square plus x square by y square. So if we do it, so y square will go,
Y
so y
upon
by.
y square. Okay.
Okay. So similarly, you can do
Sorry.
other partial derivative. Okay, is that clear?
Yes. Yes.
Okay, great. Yeah.
Sir, solve with us question 9.
Pritam, right?
Yes, sir.
Okay, let me ask some other their doubt and then I will come back to that.
Okay, sir.
Okay. Okay. Yeah. Sneha, Arun, you have also read.
Sir, activity question 11.2, question number 7.
Okay.
Mm.
Hmm.
Sir, I found the integration and I got the value of a as -3 and b as 3. Is it right? I don't get how to solve this problem.
Okay. So basically, you have to find the maximum value of the function. So first of all, you have to find the function. Right, so let me write 3 minus 2x minus x squared dx. So let me see. F of AB, it is written as A to B. Is this the function given? 3 minus 2x minus x. Okay, so first of all, this is just one variable integration, so this is easy. Minus x square by 2, so that will cancel out, minus x cube by 3. And this is from A to B. So 3b minus a minus b minus a square minus b minus a whole cube by 3. So this is the function, correct?
Yeah.
Yeah. So anyway, we can simplify it if we want. So it's better to simplify it.
So I was having a doubt. Can I ask now?
Yeah. In this
While
question.
doing, yeah, yes,
Hmm.
while doing this integration,
Hmm.
I first substitute the value of b like 3b minus b square minus b cube by 3. Then I didn't do the this b minus a the whole square.
Oh,
If
sorry,
it
sorry,
like
sorry. Yeah. Sorry. I have done this mistake. Sorry. Yeah. So it is 3b minus b square minus b cube by 3 minus 3a minus a square minus b cube a cube by 3. So this is minus, so this will be plus and this will be plus. Right? Okay. So what we have to do? We have to find the critical points, right? So at first, what we have to do? F A of AB. So what is FA? It is minus 3 plus 2a
Yes.
plus 3,
Yes.
so it is a
A
square.
square.
Yes. Yes.
And what is FB?
3 minus
It is
2b
3 minus
minus b
2b
square.
minus b square. Correct? So both of these should be equated to 0 for calculating the critical points, right?
Hmm.
So a square plus 2a minus 3 equal to 0. What are the solution for this?
minus 3 and 1.
Yes, sir.
Huh.
Minus 3 or 1.
Yeah. So this is a plus 3, a plus 1. So a is minus 3 and 1. And what about b? So b square plus 2b minus
Minus
3.
2.
Again, same thing, right?
So I got b as 3 or minus 1.
Have I written something wrong here?
B square is
So it's minus b
Is the
square
minus
minus
3 or
2b minus b square minus 2b plus 3.
So I have taken
Sorry,
minus
sorry,
all
sorry.
over.
It's sorry, sorry.
So it is the same thing, right? Same equation.
Yes, yeah, minus 3.
So b is minus 3 and 1. Correct?
Yes, sir.
So there are
Uh,
four possibilities. Minus 3 comma minus 3, minus 3 comma 1, 1
so
comma minus 3,
3 and
1
minus
comma.
1.
it shouldn't it be minus 1 and 3 because
Minus 1
it's
and 3. Correct.
2b.
Why?
So because minus 3 and 1 is not
So if it is minus b, then the equation should have been b square.
No, I
minus
think
c.
it's the right. It's a fine.
I mean, these two equations are the same, right?
Yeah.
Yes, factor is a square plus 3a minus
Yes.
a minus 3 is equal to 0.
so it is same.
So it is correct, right? These
Yeah,
are the
yeah.
solution. Correct?
Yes, sir.
Yes, sir. I made a mistake.
So now can you do the rest? I mean, how to check the which one is the maximum of this?
Yes. Actually,
-3 or 1.
So let me. Yeah. Okay. So now these are the critical points. Now we can calculate which one is appropriate for this one.
The maximum means 3 times that point, critical point.
So
Maximum in terms of what? In terms
Could
of
you please
method.
complete it?
So f denotes this maximum value, right? So first of all, you have to find which one is the maxima, and then you have to put that value in the function, and you have to calculate 3 into that value. Okay.
Okay. What's the maximum in terms of, I mean,
Will you please
like,
just show it once?
Yeah.
sorry?
Can you please just show it once? This sum, entire sum.
Okay. Okay. So I mean, what we have to do next? You tell me what we have to do next. How we have to
We
check whether these critical
Sir,
points are
sir,
maximum, minimum,
we have to
saddle point?
check Hessian matrix. We have to
sir,
get Hessian.
Hessian matrix, Hessian matrix.
Hessian matrix, right? So basically, we have to find f of a, right? What is f
Yes,
of
sir, F
a?
of A. Sir,
Uh,
2 plus 2A.
plus 2a,
Correct. F of ab,
0.
0, sir, 0.
0, and f of bb,
2
Minus
plus 2.
2 minus
Minus,
2B.
yeah.
minus 2
Minus
minus
2
2.
minus 2B.
Correct. Okay. So this is a comma b. Okay. Great. So for the first point, f of a of minus 3 comma minus 3. What is this?
Minus 3. Minus 9. No, no, no.
No,
2.
2 minus 6,
Yeah.
right? So it is
So
minus
minus 4.
4.
Minus 4.
Yeah.
And f of bb minus 3 comma minus 3. What is this one?
6
Against
minus 8.
minus 8. Correct. Okay. So let me see what. So if I go again to this solve with us thing. So here what we have to check is critical points. Yeah. So if a double derivative of with respect to x, a comma b is greater than 0, then it is minimum. If it is less than 0, then it is maximum, and determinant of the Hessian should be greater than 0, right?
Yes, sir. First, we have to check determinants.
Huh.
I guess.
So let me write the determinant. What is determinant? So the matrix is minus 4, 0, 0, and minus 8.
So F
So
of
it is
B will be 4, not minus 8.
Why?
so it is plus
4.
6, minus 2 plus 6, so it is 4.
Yeah.
Correct. Correct. So it is minus 16, right?
Yeah.
Determinant is minus 16. Correct. So what is written here?
It's
So
a
it's a
saddle point.
saddle point, right?
Saddle point.
Yes.
It's a saddle point. So this is how we have to check. Okay. So for the second point, can you tell me what are these values? If a now second point is minus 3 comma 1. What is this? 2 minus 6. So again minus 4, right?
Yes, sir.
And this is
So 1
minus 2
Minus
minus
4.
2.
minus
So minus 4.
Minus 4.
Correct. So
is
this is minus 4, 0, 0, minus 4, right?
Maxima.
So this is 0 and this is 16.
Maxima.
So this is greater than 0, this is less than 0. So let me see what condition it is
Maxima
satisfying.
it is.
This is a
Sir, this
maxima, right?
condition satisfied.
So this point is a maxima, local maxima. Okay, let's check for other two also. 1 and minus 3. 1 minus 3. What is this one? 2 plus 2a, so it is 3. What is this one? So this is plus 6, so this is 4, right? So if I am doing some calculation mistake, please let me know. Okay. And this is also greater than 0. So what is this point?
This is
Minimum.
minimum.
This is the minima, right? So this is the local minima. Okay, and the last one, 1, 1. What is this? 2 plus 2a, so this is 4. This is, I think, minus 4. And so this is 4, 0, 0, minus 4. This is minus 16. So again, it is less than 0. So this is a saddle point.
Saddle point.
Right? So there are two saddle points, one minima, one maxima. Now maximum we get at point minus 3 comma 1. Right? So minus 3 comma 1 will give me the maxima. This is the local maxima. So what is f of minus 3 comma 1? We have to put the value here, right? Minus 3 comma 1. So can someone write it? 3b minus b square. 3b minus b square minus b cube by 3.
And negative of that with a.
Huh. And negative of that with a. Right? So this is f of a comma b. Now, so we put the value minus 3 and 1 here. So 3 minus 1 by 3 minus, this is plus 9, plus 9 minus 27 by 3. Correct? So 18, 21, 20 minus 28 by 3. So 60 minus 28 by 3. So what is this value? 32. Okay, so this is your value m. Correct? You have to find 3m. So what is 3m? Is it okay?
Yes, sir.
So have you got how to solve this type of problem?
Yes, sir.
Okay.
Yes, sir.
Yeah. Great.
Sir, activity question 11.3 question number.
Who is this? Amit Kumar, is it?
Yes, sir.
Okay. Activity question 11.
11.3 question number 7.
11.3. What is it? 11 point?
Voice is breaking.
Yeah, I cannot hear you now. Your voice is breaking.
Sir, 11.3
11.3.
question number 7.
Question number 7. Okay. I think this type of problem has been discussed in the last live session, right?
Yes, sir. It's discussed.
Yeah, shortest distance of this plane to this plane. Now, you know the formula of the distance, right? So, the plane is z equal to x plus y plus 3. So, this is your plane. Suppose in 3D, I have a plane like this. I have plane like this. Now here it is origin and there is a point on this plane. So this is the distance. Now any point on this is x comma y comma z, will satisfy this equation, right? And what is the distance of this point from origin? It is root over of x square plus y square plus z square, correct? This is the distance. Okay, let me write it as a distance function then. So x, y, z, it is root over x square plus y square plus z square, right? Now z is dependent on x and y, so I can make it a function of two variable, correct? X square plus y square. What is z square? Z square is x plus y plus 3f whole square, right? Now you minimize this function. So you need the minimum distance point from it, right? So yeah, shortest distance. That means you have to find the minimum. So now you do whatever is required. You can do it from here.
Okay, sir.
Correct?
Okay.
Yeah.
Thank you, sir.
So you understand the geometry, right? What we have to do here. You can see. Yeah. Uh, yeah. So Amit Kumar is done. Krishna Mohan.
Sir, I have a doubt from 10.3, sir.
Okay. Yeah, we can discuss that also. 10.3.
So in the lectures, actually, calculation for the hyperplane tangent timestamp is around, not this one, sir, the video, sir. So I have the video is 34 minutes timestamp.
Okay. What is your doubt there?
So here, actually, the calculation part, I felt like maybe the point is 2, 3 minus 1.
So some calculation mistake is there. That is
Yes,
what
sir.
you are saying.
Yes, sir. I think I'm not sure if I'm making a mistake or if there is a mistake in the calculation there, because the sir has taken the point which is going to be 2, 3 minus 1. And
What is
but
the
in the
timestamp? What is the timestamp?
31 seconds, sir. So timestamp is 34 minutes.
Okay.
It has to be the first term is given as 3, sir, but I'm getting 14 as the first term because it's when you calculate, it should be first you find out the function that is the f of for the
This is
80.
34 minutes. So
34, yes, sir.
Okay, so CP, this was
Can
asked in
you?
discourse, and Subhash sir confirmed that there is a mistake.
maybe there may be some calculation mistake. Yeah.
I think it was 14, right? I guess. Okay.
Yeah, it should
Yeah,
be.
but you have understood the concept, no? How we have to do it.
Yes, sir. I
That
got
is
the
okay. Then that
concept.
is fine. I mean, the calculation you can do it yourself now.
Okay. So the next one is I have another one the same since we are staying here. Just for a second, it should be 14. Then AQ. Yes, sir. AQ 10.3, sir.
Okay.
Question number 2.
Okay.
So here, actually, 1 second, sir. 3. Sir, I'm not getting any of these as while I do the calculation, sir. Actually, I'm getting totally different. I'm getting a 7x minus 3y something I'm getting. So I don't know whether I'm doing it correctly.
Okay. So let me see. Fxy is given as 3x square plus xy minus 2y square.
Yes, sir.
Right? So let me write it here. Fxy 3x square minus xy plus xy minus 2y square. Xy minus 2y square at the point 1 comma 1. Right? You have to find the
Yes, sir.
tangent plane.
Yes,
Right?
sir.
So what is the equation of tangent plane? I mean, how you can find the tangent plane?
Yes, sir, the usual formulas are like, for example, we are just taking first say f a tilde because this is a tilde, a 1 and 1 a tilde, right? So, I'm taking the A tilde, then I'm taking the.
This is the formula, right?
Yes, sir. F of A tilde plus
Not f of
del
a tilde.
Not
del
18. This
del
is
F of A tilde. Del F of A tilde dot x tilde minus A tilde, right?
This one, right?
Yes, sir. Yes, sir. Same thing. F of A tilde.
I mean, more or less, if you simplify what you are saying, we will get this
Sir,
one.
I'm not getting any 5 at all, sir. I'm getting only 7 as my x
So
coefficient.
basically, first confirm this is the thing we are getting by simplification, right? So what is fx here?
6x plus y.
6x plus 6x plus y.
Okay. What is fy here?
X minus
X minus
4y.
4y. X minus 4y.
X minus 4y. Okay. So and here my point is 1 comma 1. So what is fx 1 comma 1? It is 7, right? And
7
fy 1
minus
comma 1,
3.
it is
Minus
minus
3.
3. Okay,
Minus
great.
Yes,
3.
I'm getting that also, sir.
So 7
X minus 2
x minus 1
plus 1
plus this
minus
is
3.
minus 3, right?
Hmm.
Minus 3 y minus b
Y
equal to
minus
z
1.
minus f of ab. What is f of ab? F of 1
y
comma
minus
1.
1.
2, right? It is.
2.
Y minus 1, and this is
Z
3
minus
1
2.
4 minus 2 2. So this is what you are getting, right?
Yes, sir. In the so if you simplify, yes, sir. But this is not what we are getting in the option.
So maybe there is some option which is wrong.
Option.
I am 7x minus 3y to the minus.
So this is correct. Whatever you
yes,
get,
sir.
that is correct. Yeah.
Yes, sir. So if you look at the options, it's not given. None of the options are.
Yeah. So we will correct it.
Oh, okay. I can.
Okay.
7x minus 3. But 7x minus 3y minus 2 is the correct answer, right?
I mean,
Okay.
whatever by simplification you are getting.
Okay. Okay.
Hmm.
7x minus 3y minus z, and this is
minus z, sorry.
minus 4, so 2.
Minus 2.
Minus 2. Yeah.
So please show the question.
Have I done something wrong here?
True, sir.
The point is 1 comma minus 1, that's why. Point is not 1 comma 1, 1 comma minus
Then
1.
it will change.
1 comma 1, no, sir. It's given 1 comma 1, right?
No, 1 comma minus 1 it is given.
Minus 1.
Okay. So, yeah, we will get back to here. So this is 6 minus 1, this is 5. And this is 1 comma minus 1. So this is
5.
basically this is a calculation. I mean, why are we doing it here? So this is 5, right?
Yes.
And what is 1 comma minus 1? So this is 5. This is okay.
Okay, so
this is 5,
sorry,
this
I
is
think
plus
1 minus 1. I didn't take it at 1
0.
minus 1. I made a mistake.
This is 3 plus. This is
0.
3 minus 1 and minus 2. So this is 0, correct?
Hmm.
This is 0. So this is 5x minus 5. This is plus 5x, 5y plus 5. So what we are getting as the equation?
5x plus 5y minus z equals to 0.
Is there an option like this?
I think 5, it's there, I guess. Maybe
Yes,
so I think I made a mistake
Option
in 1 and minus 1. Sorry, sir.
Yeah, okay.
So there's one more thing, just one doubt. This is conceptual doubt. Just a conceptual doubt. So we could say that from the lectures, what I gathered was the tangent plane and linear approximation are the same, right?
Yeah, exactly.
Okay, thank you. Thank you, sir. Thank you.
Yeah, that was same for the one variable calculus also, right? Tangent line will give us the linear approximation, basically.
Yes, sir. Thank you, sir.
So here also it's, yeah.
Thank you very much.
Yeah. Okay. Yeah, so Amit Kumar, I will get back to you later because I have already answered your one question. Yeah, Amitabh Bhattacharya.
Hello, sir. Do you able to hear my voice?
Yeah, very lightly, but okay, go ahead.
Now?
Yeah, now I can hear you. Go ahead.
Okay. So, uh, sir, I have a very conceptual doubt. Okay, so my doubt is 11.4.
Mhm.
So actually, I am not getting that why the second option is not correct. So maybe I have some problem with this differentiability things. What do you think?
Were you present the first half of this live session? I mean, I have already discussed 11.4.
Oh, sorry, sir. I have attended maybe 10-15 minutes late.
So basically, you know how to do the differentiability, how to check the differentiability, right?
Yes. So is it
Uh,
checking the partial? Okay. So okay, you can go ahead. Okay.
so yeah, basically, I will prefer to use the definition of differentiability. If this limit is zero,
Hmm.
you can see this, right? If this
Yeah.
limit is zero, then we can show this. So we have checked for option 3.
Hmm.
Okay, and we have shown that this limit is definitely is going to zero indeed. So the function is differentiable. I mean, not differentiable is not going to zero. And in case of second option, it is more clear. Now, for a function to be differentiable at some point, first of all, you have to check the continuity of that, right? If
Hmm.
it is not at all continuous at that point, then there is no point of checking differentiability, right?
Hmm.
Now, is this function continuous as zero? The second option.
So I'm not sure, sir.
Why?
Oh,
I mean,
but
does limit exist at
no,
0,
no, no.
0?
So I have some conceptual gap actually here. Maybe I
Okay.
am not. Okay.
So let me do it for you. So the function second option which we are taking here is this one, correct?
Mm-hmm.
So this is not origin, and at origin it is 0, correct?
Mm-hmm.
At origin. Okay. So what is continuity basically? Continuity means if this limit, if we want to check this limit, suppose we want to check the continuity at the origin. So xy is going to 0 comma 0. When we approach towards this point 0 comma 0, that should be equal to the functional value of the function at that point, right?
Oh, so if I take the y equal to mx, yeah.
So in this
Okay.
case, this limit does not exist at all, right? When we are approaching towards 0 comma 0, this limit does not exist because if we take the, as you are saying, if we take the car y equal to mx,
Mx, yes.
right? For different m, we will get different limit, right? So the limit is not unique. So that limit cannot exist, right?
Yeah.
Because for existence of limit, that should exist. I mean, that should be unique. But that is
Okay.
not the case here. So anyway, this limit does not exist in this for this function. So f is not continuous at origin.
Sir, this is equivalent to saying that right hand limit is equal to left hand limit, right?
Here there is nothing called right hand and left hand because here we are approaching for different direction, right?
Then how can we understand that when we will need right hand limit, left hand limit, and
Right hand limit, left hand limit is only for one variable function, right?
okay.
Because they are for one variable what you are doing. This is your curve, right?
Yes.
Whatever the function you are getting, the graph will be a curve, something like this,
Yes.
right? So at some point, suppose I am want to take a limit for this, I can approach it from left hand or right hand. Only these two directions are possible, right?
Yes.
Now, in case of multivariable function, I mean, suppose two variable function, this is my graph will look like, right? This is the surface.
Yes.
Our functional graph will look like this. Now, there is my point, right? A comma B on xy plane, okay?
Hmm.
And on the z axis, we are plotting the functional value, right?
Yes.
So here it is f of AB, correct?
Yes.
So if I want to approach this point, can you see there are more than just left hand and right hand? There are many directions from which we can approach the point.
Yes.
There are basically infinitely many directions,
Yes.
right? So there
Yes.
is no concept of right hand or left hand limit. Here the concept is if we come to this point from any direction,
Okay.
all the directions, I mean, all the limits we are getting that should match.
Okay.
Okay, not only left and right. From
Okay.
any direction, we have to show that.
Okay.
Now there are infinitely many directions, so we literally cannot show by using that thing, but we
Yes.
can disprove something using that, right? If you
Yes.
can find two straight line, one is suppose y equal to x, like in this case, suppose y equal to x, we are approaching on this line, or some along this line. Then if from these two directions the limit is different, then we can say Okay, the limit is not unique from these two directions, so definitely the limit does not exist. Got it?
Yes.
Okay.
Sir, I have another doubt. Okay, so maybe
First of all,
same.
this is clear. Is this clear?
Yes, this is clear actually.
Okay.
So okay, so now my second doubt is the practice assignment point 5. So
Practice
I am
assignment.
5. So I am actually get very confused with this type of questions actually.
So today we have uploaded the solution of practice assignment. Have you seen it?
Okay. So actually I have asked it, so I have not checked it last 2 hours. So
So
maybe
what is your doubt here?
no. So so from here I can found that fx I can easily found because limit h tends to 0, f of x plus h y minus f. Okay, from there I can get the value is 0. Okay,
Okay.
similarly if y plus y I am getting the value is 0. Now how this is coming that fxy at 0 equal to -1? So maybe I am missing something here. Maybe my
So
concept.
suppose I further take the first one, fxy 0 comma 0. We have to find that.
Mhm.
So what is this? fxy 0 comma 0. So first we are differentiating with respect to y, then we are differentiating with respect to x, right?
Okay.
Okay.
Yes.
So basically limit h tending to 0 fx. We have already differentiated with respect to s. Now we are differentiating with respect to y,
Mm-hmm.
right?
Mm-hmm.
So this is the first variable. This is the second variable. This is fx 0 comma 0. Right, this will give you, sorry, this is fy, and then we are this one.
Mm.
Is that okay? This is differentiation. So now my function is fy,
Mm-hmm.
and I am differentiating this with respect to x. So what should I write?
So fy I got it 0. So maybe there I am wrong. Fy 0 is 0 for me.
So maybe that happened, no? What
Okay.
is problem with that?
Okay. Then
Fy
why?
0 0 is 0, but what is fy h comma 0? That you have to find.
Okay. So how I
That
find
is
it?
not, that may not be 0 comma 0.
So how I?
I mean that may not be 0.
Sir,
So you know what f is, right?
Hmm.
You know what fxy is when it is not origin. You differentiate it with respect
Okay.
to
Okay.
y.
Okay. Then I need to find fy for that.
Yeah.
And
And then
then I
put
need.
h comma 0 there.
Okay. Got it. Okay.
sir, just a small clarification, sir.
Huh.
Yeah, like here fxy is written, so it means earlier we have differentiated with
So
respect
what
to x.
convention Sarah has taken, you choose that. Okay. I may have messed up the convention.
Okay, no problem.
Okay. So
By
what
going
convention
by
it
that
is taken in lecture?
going
First
by
y,
that
then x.
logic, it will be fx. Where we are writing a limit h tends to 0, so it will be fx, sir. Because now
That is
earlier,
fx. So this is basically first we are doing y, then we are doing x.
No, sir. First we have to
First we
differentiate
are
with x
doing
and
x,
then.
then y.
yeah,
Yeah.
first
So
yes,
First with x,
let me
then with
take, this
y.
is yx.
yes,
Now is it okay?
yes.
Yes.
Yeah. Okay. Great. Yeah.
And sir, just in the
Anyway, for continuous function, this doesn't matter actually, right?
okay, no problem.
Because Claira's theorem says that.
I was just
For
clarifying my
continuous
doubt, sir. Nothing
Yeah,
else.
sure.
Sir, just
Sir.
two lines up, sir. Okay. Let him
Huh?
complete. Then I will ask. Someone is asking. Okay.
Yeah.
Sir, you
Yeah, Amit.
practice assignment 11.
Practice number 11. Have you solved
Yes,
it yourself?
yes, sir. Yes, sir.
Okay.
Yes, sir. Question number 2, sir. Question number 2, I have some doubt about concept.
What is your doubt?
Sir,
Yeah.
question number 2, I have solved this question, but
Huh?
the value d at 0 is the 0. Then how is 0 is the local minima? Sir is giving the
You are
0
getting
is the point
D
of
of 0
local
0 is
minima.
0.
Hmm.
Yes, sir. D of 0 is 0. So this is a case of
Not conclusive, right? That's
Yes.
what
So
your point
yes,
is.
sir. Yes, sir.
yes.
Huh?
So the
Then
in the
yes,
forum
sir.
they have Sarah's giving the solution. So that was my question also.
So basically, if you see that the function is x power 4, so using the test, it is showing that d of 0 0 is 0. So from the test, we cannot find, right? But x power 4 plus y power 4,
Yes, sir.
can
Yes,
this
sir.
function be Negative anywhere?
No.
No, right? And what is the minimum value of this
No,
function
sir.
can be? What is the minimum value of this function can be?
0.
0, sir.
0.
0, right? And when that occurs?
0, sir.
0, 0.
At 0, 0. So, by seeing this
Yes.
function, although we cannot conclude it from the test given, but by the pattern of this function, we can say that at 0, 0, 0, 0 is a critical point, that we know for sure, but we cannot determine using the test whether the function is attaining maxima or minima there, but we know that at that point 0, 0, it must be a minima, right? Because the function cannot go below that. Is that okay?
Okay, sir. Sir,
Is it clear,
also
no?
in question number 3, I had yes, sir, yes, sir,
No,
clear.
first of all, tell me, is it clear or
Also in
not?
clear, sir, clear.
Okay, good.
Can-
Yeah.
Sir, question number 3, sir. Question number 3, I have also.
Amit, you go and see the solution first, okay? Otherwise, you will ask all the question one by one. Okay?
No, no, sir. I have solved this question, but
Okay, what is your doubt here in question number 3?
sir, 3, 4 is the point of absolute maxima. Option number B, sir. This is not satisfied.
This is not satisfied with what? I mean, it may not be a critical point, but it is on the boundary, right? So first of all, what you have to do, you have to find all the critical points here and see what are the critical points. And then you have to check along the boundary also, correct? You remember for one variable what you have done? You have to find first of all f dash x where f dash x is becoming 0. All those x you are finding. That is your critical points. Now you have to check along the boundary also, right? Along the boundary points. If along the boundary some maximum value is coming which is greater than the local maxima, then that will be your absolute maxima, right? Global maxima.
Yes, sir.
Got it, no?
Yes, sir. Yes.
Okay, great.
Sir, could you please come to notepad, sir?
Yeah.
Yes, this diagram, sir. When you were explaining with respect to one variable, sir. So here I have a conceptual doubt, sir. Sir, basically we say that at a point, say for example A, right? If limit exists at that point, means value of the limit and value of the function, if they are same, then only we say that it's a continuous function at that point, and then we calculate the differentiation, right?
Exactly.
But while doing the differentiation by first principle, we directly write that f dash a equal to limit s tends to 0 f a plus s
No,
minus f a.
1 minute. What I have said is, if the function is not continuous, you know that some function is not continuous at that point, there is no point of checking for differentiability. Because differentiability implies continuity. So if it is not continuous, then there is no point of checking differentiability for that function.
Okay, so that is understood, right?
Now, if you want to check using the first principle, you can do that. Still, you will get that the function is not differentiable.
Okay, so that is understood, right? That is hidden.
Not hidden. I mean,
But means
first
understood.
principle
Okay.
will always work anyway.
Correct. That's
But
understood.
I am saying that you are basically that is not needed to check because you already know the function is not continuous.
So that's the reason why we directly start doing calculation, right? If
yeah, right.
F a plus s minus f a, right? By a limits s tends to 0.
Yeah.
Okay.
Sir, existence of partial derivatives does not imply that the function is differentiable at a point.
Existence and continuity implies the function is differentiable.
So is
not
it
only
same?
Existence.
So is it same or is it a stronger condition, like the partial derivative and the continuity?
I mean, partial derivative may exist, but it may not be continuous, right? So in this example, what we have seen here, the first one, this one. So if you check this partial derivative with respect to x, this exists. Anyway, this exists. This is the partial derivative, right? And also at 0, 0, it exists. It is 0. But you can see that at 0, 0, you can see that this function is not continuous. So the first order partial derivative is not continuous at 0, 0. That's why it is not differentiable.
But
Yes,
in
because in
one
the
variable
definition,
calculus,
because in the definition of the differentiation, we are taking the gradient vector gradient. So for the gradient to even exist, it must exist. The partial derivatives must
Only
exist, and
existence
it
is
must be
required.
continuous.
There, in the definition, it is not taking care of the continuity for using the definition only.
But when I'm taking gradient, gradient is defined when it must be continuous, right? The partial derivatives, or it should exist. Just
I mean, at 0, 0, we are taking only, no? So we don't know whether it is continuous or not at that point. But when this limit altogether, this limit altogether is going to 0, then it implies that this partial derivative is also continuous. But only the existence of gradient does not imply that this is all the partial derivatives are continuous. That only implies it is the existence of the partial derivatives.
okay.
Okay.
but in one variable calculus, the derivative was not present if the function was, I mean, the derivative would not have been present if the function was not differentiable at a point in one variable calculus. If
So
a function is not,
here also we are not talking about derivative anywhere. This is
a
gradient.
derivative is equal to gradient, no, sir, in two variable, multivariable
No, who
calculus.
has said that?
Okay.
No. I mean, how we get this thing? Gradient is a different thing. Gradient is basically the normal direction to the tangent plane.
Okay.
Gradient is a vector.
But we are differentiating when to find the
There is a
gradient. We
concept
are
of total derivative in multivariable, but we have not discussed it anywhere till now.
okay. Okay.
Okay, there is a concept of total derivative, but this is not in this course.
Okay.
So here we can only check whether the function is differentiable or not. Till that we are stopping here.
Okay.
Okay.
So to know whether the function is differentiable at a point, the gradient should exist as well as the gradient vector gradient should be continuous at that
All the
point.
partial
Only
derivatives
then
should be continuous. Exactly.
continuous. Okay.
Exactly. Okay. And for one variable, what you are telling is right. If a function is differentiable, then there is a derivative. The derivative exists. That is true.
Yes, sir.
But for multivariable, this is, I mean, we are not talking about derivative yet.
Okay.
Okay.
So gradient
We
is
are
not
only
equal
talking
to
about
the
partial derivative. Partial derivative are not equal to the total derivative. Total derivative is a different volume together.
Okay.
Okay.
A similar equation in one variable calculus, instead of the gradient, we would have the derivative, right? Instead of the
Right.
gradient, we would have the derivative multiplied by h in a similar equation for in one variable calculus.
So,
No, for one variable, how we are checking the differentiability? Do you remember how we are checking the differentiability for one variable calculus?
The derivative was equal to f into f a plus h.
So basically what we are getting there, that is the derivative, this limit, right?
Yes.
F of a plus h
A plus h minus f a
Plus,
by h. This is defined as f dash a. When this limit
yes.
exists, we said that this is differentiable, and whatever the limit value is, the value of this limit is, that is your derivative at that point.
Derivative. If you take the derivative to left hand side, then we'll get a similar equation to the one above.
Exactly.
Only thing
Anyway,
the
that is
gradient
the
would,
point. That's how we generalize something from one variable to multivariable. That is the point. But remember, this is not exactly the total derivative of the gradient is not the derivative of the function. Okay, in multivariable. That is not the case. Okay. Okay.
Being continuous, it is differentiable. We can
when we
deduce
are
that, right, sir?
One by one.
It is continuous. You are saying, sir, you are saying earlier, like back, like it's continuous. So if it's continuous, we can deduce that it is differentiable, right?
No. I am saying whether all the partial derivative exist and all of them are continuous at that point. Then it is differentiable.
Okay.
All the partial derivative. Okay.
Okay.
So when we are earlier when we were finding the directional derivatives, then when you use the formula that gradient into u, then the partial should exist and it must be continuous, right?
Where?
The directional derivative, when you are using the formula that gradient
Right,
into
right,
u,
right.
then in that the partials should exist and they must be continuous.
Exactly.
But for the gradient, just for the gradient to exist, only the partials need to be existing at that
Because
point.
gradient is just fx and fy at that point. So
Okay,
you can at that point, if it exists, then we are through.
Okay, so when the gradient is existing and continuous, then it's a stronger condition and it must be differentiable.
Yes,
but just by the definition of the differentiable, we are not considering that the gradient is continuous.
What does last line mean?
But just from the definition, like the definition that you
Definition
have
of
written
what?
of the differentiability.
No, if a function is differentiable, I mean, if this limit is 0, then we can say the gradients are continuous. I mean,
No,
partial derivative are continuous.
Yes, but I'm not saying that whether I have not yet checked. I'm just saying that the writing the definition, I'm not taking into consideration that it must be continuous. It is just existing of the partial derivatives. I can write the gradient of that.
Yeah, exactly. Right.
Okay.
Right. If this whole limit exists and it is 0, then
it
only
is
we can
continuous.
conclude. Right.
Okay.
Okay. Got it, no?
Okay. Yeah, yes.
Okay. Bhupesh.
Yes, sir. I have a doubt in graded assignment 10, question number 7.
Okay, but graded assignment solution is given, no? Have you checked that?
Sorry, I did not check it.
So you should check there at first. Okay, let me see what is your term. Graded assignment question number 7.
7.
Okay. So temperature at the point, rejection towards the point this. Find the value of 10
My answer was like minus 160 because I had to multiply by 10 also, but in actual the answer is minus 16.
Okay. I mean, this is calculation. So can you check the solution?
Yeah, I'll check
You have to calculate the directional derivative, right, at that point.
Yeah, I'll check the solution.
So this is calculation. I mean, conceptually there is no issue there, right?
Yeah.
You know what you have to do.
Yeah.
We'll check the solution. Okay. Pritam. What's your other term?
So solve with us question number 9.
Which
week 11. Week 11.
Okay. Solve with us question number 9. Yeah.
So if I'm not wrong, 5,0 is a point where the Hessian matrix is 0. So how do we conclude that? Yes, sir. Could you please check it?
Okay. So basically I have to do the calculation again. So can you tell me what are the calculations here? I mean,
yes, sir.
No, if it is 0, then from this function we cannot say directly that whether it is local minima or not. I mean, the test is inconclusive. You are right.
Yes, sir.
But have your all of the calculations are correct?
Yeah. So could you please confirm it? Okay. Let us do it. So it is 6.
So can you do one thing? You put your calculation in Discord. So we'll check it there. Otherwise, the time of live session will be wasted.
Okay, sir. And same solve with us question number 12.
This one, right?
Yes, sir. For this, when you click check answers, it in the targeted feedback it is said to apply L'Hopital's rule. So I could not. Here it's not there.
No.
How? Just a minute, sir. Let me check.
Which option it is coming?
1 minute, sir. Just let me check. It was showing me.
I think for three, option 3 it is coming maybe.
This is question number 12. Yes. Targeted feedback is use L'Hopital's rule.
For which option?
It's not clearly written which option. Sir, can you mark the first and fourth options and then check answers?
Yeah, now it is coming.
Yeah. Yes, sir. So
Okay,
I couldn't
so maybe
understand the
it's for
rationale.
the third option. Maybe whatever I am remembering, it's for the third option.
Okay, sir. So how to use L'Hopital here and where to use?
Mm, okay. So for third option, what you are doing for the third option? I mean, if without using L'Hopital tool, if you are getting everything done, then it is also okay. You don't have to use that.
Yeah, I'm just curious how to use it.
Okay, so suppose in some sense, I mean, what I remember from here, at some place we can take only one function. I mean, we are taking h1, h2, right?
Yes, sir.
So at some place we have to fix one h2, and it will be function of h1 alone. Then you can use L'Hopital tool there.
Okay, sir.
Okay,
Okay, sir.
that was the point basically.
Okay,
So
sir.
even if without using that it is coming, then it's okay. No issues there.
Okay, sir.
Okay. Yeah. Okay. Yeah. Advait.
Yes, sir.
Yeah.
Sir, hello. Sir, I'm struggling with finding the limit of this multivariable calculus. I'm not able to get it. Like, for example, when I check the solution, it says that
Hmm.
let's approach the line from y is equals to mx.
Hmm.
So, how did we get that? And is there any other shortcut method? Like for first one variable, we had like a hospital rule. So, is there anything that we can apply here?
No, here directly those kind of rule may not be applied directly. But yeah, sandwich theorem is one thing which you can apply anywhere if you want. And so you understood the approach. I mean, what does it mean by taking y equal to mx line there? And why are we taking those kind of curves? Do you understand those concepts?
No, sir.
Okay. So this point is clear, what I was talking here.
Yes, I could
Huh.
understand like in pieces.
Okay. So suppose in one variable, what we are doing when we are approaching towards some point, there are only two directions, right? Either from left or from right side, right? But
Yes,
if
sir.
we approaching a point in our two variable, so suppose there is my point a comma b. So there are infinitely many directions by which we can approach this point, right? Infinitely many directions we can approach this point, correct? And if
Yes,
limit
sir.
exists, by approaching any direction, approaching from any direction, all the limiting value should be equal, correct?
Yes, sir.
That is the basic definition of limit, right? From whether we are approaching to that point, all the limiting value should be equal. Now, suppose for some function, we can find two different curves for which the limiting values are different. Then we can conclude that limit does not exist, correct?
Yes, yes.
Is this portion clear? Okay.
Yes, sir.
Now, suppose I have a function like this, okay? Okay. So, this is when xy not origin. And when it is origin, we are taking 0 comma 0 at origin. Suppose we have this function. This is one, I mean, famous example basically. So now what we are doing, so we have to approach the origin, right? 0 comma 0 from different direction, and whether the limiting values are same or not. Now, suppose we have this type of equation where this xy by x square plus y square. What is the degree above?
2.
2. And what is the degree below? This is also 2, right?
2. Yes,
So
sir.
this type of equation or this type of function is basically called homogeneous function. Okay. So if you don't remember this name, it's okay, completely okay. So if you check these two degrees are same basically, so there is a possibility that limit may not exist because there may be some curve by which you can show that the when you approach by those curves, the limiting value will be different. So suppose I am taking y equal to x, this straight line. Y equal to x is passing through origin, right?
Yes.
So if I approaching via this straight line, what I will get? So if I put y equal to x, so I will get x square. At the denominator, I will get 2x square, right? So this is half.
Sir, you
So
get
this is
x
always
cubed, right?
half. Huh?
X cubed.
No, xy by x square plus y square.
No, sir, you would replace y with. Oh, yeah, okay. Yes, sorry.
Y equal to x. So it
Yes,
is
yes, yes,
x
sir.
square by x square, so it is half. Okay. So whatever the value of when we are approaching towards 0, so if I take limit xy going to origin via this straight line, we are getting the limiting value to be half. Correct? Is that okay?
Yes, sir.
Okay. Now what happens if we take this straight line? This is another straight line which is passing through origin,
Yes,
and we
sir.
are putting this same thing. So this is y equal to 2x. So 2x square by x square plus 4x square. Correct? So this is 2 by 5. So when we are approaching via y equal to x, we are getting half. But when we are approaching via y equal to 2x, we are getting 2 by 5. Correct? So the limiting value is not unique for these two straight lines. So what we can conclude? We can conclude
Limit
that
does
at
not exist.
0, the limit does not exist, right? Now, what we do when I am taking y equal to mx directly? Basically, we can vary m. Like here m is 1, here m is 2. Here we are taking infinitely many straight line and do it in a direct way. So, what we are doing here? 0, comma 0. So, mx square x square plus m square x square, that means m by 1 plus m square. So if you change the value of m, you will get different values for the limit, like we have got for 1 and 2, right? That is the approach we are taking. Now, not if, even in some cases it may happen that from all the straight line the limiting values are same, so we are getting same limiting value. But that does not guarantee, because straight line is one of such curve. There are infinitely many possibility of those curve, right? The curve may not be a straight line at all. It may be a hyperbola, maybe a parabola, anything it can happen, right? Maybe on some arbitrary curve. So some cases it can arrive, we have to choose different curves. So that depends on your practice, how you can get those curves
But then how to
and your
rule out that?
intuition.
Sir, how to rule out that?
How to rule out that?
Like for this, you extend y equal to mx
You
with
have to
respect.
check the degree of the numerator and denominator. That is the only way.
Okay, so it's
You have
like
to check the
in
degree
this
of
in
numerator
this
and
case
denominator.
degree is same, right? So we are saying that's a homogeneous equation, and then
Then
probability
straight line generally works in this type of equation.
then probability is very high that it may not be a continuous, right? And what about if
Right.
denominator degree is more or denominator degree is less? Then what should be our
That
approach?
depends on different type of problem. That's what I am saying. I mean, there is no thumb rule. What I can say here directly. Okay, you have to check it from the sketch, and by intuition you have to do it. Okay.
So here when we have already defined the function, that function at 0 0 is 0, right?
Mm-hmm.
So
Mm-hmm.
doesn't it mean that now the function is continuous?
Why? The limit does not exist at 0, comma 0. So how it can be continuous?
Okay, so the value of the function is given, right?
I mean, if is this function continuous in one variable? Is this function continuous at one variable?
At 0?
At 0?
No, sir.
No, why?
Because we are getting 2 and the value of the function is 0, so it is
The
not
same thing
continuous.
happening here.
Okay.
I mean, here even more thing happening here. Here the limit at 0 does not exist at all.
Yeah, value of the limit is 2, so limit exists, but it is not matching with the value of the function at 0, right, sir?
Yeah, exactly.
Okay, thank
you. Okay. So by defining a function does not guarantee that limit exists at that point.
Okay, that element of doubt came to mind, sir. Thank you.
So yeah, Advait, is it clear? I mean, how we are taking the limit and why we are taking these curves?
Yes, sir. It is clear, but can't we use
You have to
anything like
practice it. I mean, there is
partial
no
derivative
thumb
or
rule
anything?
why you have to, I mean, how you have to approach a problem. That I can say.
So, sir, can't we use like partial derivative or anything to calculate it?
No, no, no.
Okay.
Limit is a different issue. I mean, so in general, some specific curve, I mean, y equal to mx, y equal to mx square, I mean parabola, or say x equal to, so y equal to root x, m root x. This type of curve generally works. Okay, you don't have to
Okay.
go beyond that. Generally, this type of curve works if limit does not exist. Otherwise, you have to you have to try to prove the limit exists and find out the limiting value. That is using the, I mean, what I should say, sandwich theorem or inequality. You have to use all those things to get the limit. Okay.
Okay. So when we substitute all these equations and curves, so it should be independent of m.
It should be dependent on them.
Sorry, that means it should not have any m.
No, I am saying in these cases, if you replace this curve, if it is dependent on name, then limit does not exist.
Yes,
If
sir.
limit exists, you cannot use all this technique. Then you have to use your squeeze theorem or sandwich theorem or inequality to show it.
Okay.
Okay. Is it clear now?
Yes, sir.
Okay. Okay. So if there is no doubt, I was planning to show you some Geogebra application here. So have you seen how directional derivative actually look like? I mean, what does it mean? So suppose, can you see it?
Yes, sir.
Yes, sir.
Okay. Okay. So this is the function x square plus y square by 2. Okay. So first of all, by seeing that, so this blue thing is the curve of this function. So first of all, can you tell me what is one of the local minima you can see from here?
It's
0, 0.
origin.
0, comma 0, because it cannot go below that. So 0, comma 0 is definitely a local minima. Correct? And that is actually a global minima anyway for this function. Okay. Now I am taking a point 1, comma 1 as we have uh, pointed out here, 1, comma 1. So at 1, comma 1 the functional value is half. So this is the point we are taking, 1, comma 1 here, and the functional value is here on the curve, on the surface. Okay, and I am taking this vector u. So this is my vector at this point, and we are trying to calculate the derivative of that directional derivative of that function. I mean, how it looked like. So if we see, suppose we fix the point 1, comma 1. Now if we change the direction of the vector, you focus on this arrow, okay, this vector. So if you change the direction of this vector, you can see this line, this will change, right? The directional derivative will change accordingly. Correct?
So where is 1, 1 point? Just got confused.
1, 1 point is on xy plane, right? Here.
Yes. Okay. Yeah.
This P point is 1, 1. Okay. Here.
U
And this
the
is the
direction of
functional value at that point. So this is 1, comma 1, comma half.
Yes.
Correct?
Yes.
Okay. Now if we change the direction of this vector, this is my vector direction at the point 1, comma 1. If that changes, then this line, you can see this line, right? This direction, this line will change, right? That is due to the direction derivative is changing at that point.
Sir, I'm getting the direction, how the direction of this vector is changing, directional derivative, but how the length of it is changing?
No, length is not changing. Length is,
Yeah,
I
it
mean,
is changing.
this is
Na?
straight
F
line,
dash
it
of
is
1.1.
infinite.
No, I'm saying, sir, f dash of 1.1 is changing, na? that is 1.73 to 2.2 or something like that.
This is directional derivative, the value of the directional derivative at that point.
This is the length of the vector, no?
Directional derivative is not a length.
Directional derivative is a vector, no, sir? If I take out the length of that vector, it will be this much, no?
What?
Directional
What is
derivative
directional derivative? First of all, okay, let me stop it. What is directional derivative? I mean, what was the definition of directional derivative?
So basically, we are restricting f in that direction, and we are asking for the change of f in that direction.
The rate of change at that point along the direction.
Yes, so rate of change will
the rate
change,
of change,
no?
that is a scalar value. That is not a length.
So it's a scalar value, sir? Yeah.
Rate of change, what does mean rate of change means? Rate of change means a scalar value. It will give a scalar value, right?
Rate of change can be vector, no, sir? Vector.
I mean, why are you saying that directional derivative is a vector?
For a particular point, it will a scalar value. When for a general,
Because it has a direction, it has a value, and can be represented as a vector. That's what I'm saying.
No, that is different issue. So I am saying what is rate of change? Rate of change is a scalar value here, right? What is directional derivative? Suppose I am taking a point A1, comma A2, okay? And along this direction, unit vector, suppose this is unit vector, U1, U2. What is the directional derivative FUA? What is this? What is directional derivative? You remember, no? What is this one? This change, right? This is the increment by age, right?
Yes, sir.
Yes,
so
sir.
This will give you a number, right?
Yes, sir.
Is it okay, no?
No, sir, actually. Why it's not okay? Let me, because it will change on the, depends on the U, right, sir? U and A. Like
that is why this value is changing. Yeah, exactly.
So directional derivative as a whole, so directional derivative at a point is a scalar value, but directional derivative like as a whole, right, sir? It's a vector.
That is a function.
Yeah, that is a function, no? So
function on xy, exactly.
So
yeah, so that's what at the beginning I was saying.
Yeah, here I am saying, sir, this value is changing, but how is it reflected on the graph? This change in value, 1.73 to 2.2. Let's say if you change the angle, can you just change another angle? Yeah.
Yeah.
So how is
this value will change, no? Because
yes,
U is changing. Angle is changing means what? The vector is changing. So it depends on the vector, correct?
Yes, sir. Depends on the vector. So
if vector is changing, if this direction is changing, then the rate of the change of this function is also changing, because you can see the curve of this function, right?
Yes, sir. I'm saying, sir, if you check the red line, sir, red is the directional derivative, right, sir?
No, red is the vector along which we are taking the directional derivative.
Okay. I got it, sir. Okay. I was mistaken. Yeah.
Okay.
Okay, sir.
So this straight line, this slope of this straight line is basically giving with this directional derivative.
Okay. Sorry. Yeah.
Okay. So the slope of this straight line changes, as you can see. Now the slope is negative. Okay. Now this slope is positive.
So while staying with this GeoGebra, so this is quite different from what we are seeing. Actually, this looks better, sir. How did you get this?
I will send you this. Okay, I will send you these links. Okay.
Yes, so please send the links, sir, because the actual one was quite difficult, but this is much more clear, sir.
Okay. Now, so one thing, it depends on the vector, that is clear, right? Now, if we change the point, then also, so I am changing x and y coordinate, then also this direction derivative will change, right? Because at different point, if we fix the vector, still the rate of change will change. I mean, rate of change will, that will be changing, right? You can see.
Yes, sir.
If we move the point along this curve, the direction of the vector remains fixed. I am not changing my vector u now. Still, the rate of change will be depending on this point, right? So the direction derivative will change. Is it clear? So I can also change the x coordinate. So it will go that side of the function. It is coming this side of the
Yes, sir. When
function.
I was saying actually the length of this actually, so I meant if I take a vector, if I take the vector of that black point, right, black dot from the center, that length is actually changing, right? And that is actually reflected by f dash of 1.09, right?
No, f dash is basically the slope of this straight line together, not only the length. The slope of the straight line.
Yes, sir. Yes.
Derivative does not, nothing to do with the length. It has to do with the slope, always.
Okay, sir.
Okay. So what is basically it is doing? I am fixing a point. So you can see this black dot. Now where I have put my cursor, right? This is my point 1, 0.9, right? And the functional value, whatever the functional value there. So this is 1, 0.9, f of 1, 0.9. Right? This at this point, how the slope of the curve changes in this direction, in this red vector direction, vector u. Right? So what we are doing here, basically, the slope of this straight line will give me the rate here. Now, if we change this point, if we move this point, the slope will be changing, right? Because we will get new straight line at that point, passing through that point along this direction. Okay. Now, if we change the vector, again this line will move. For different direction, different vectors, and different point, the direction derivative will change. So basically, direction derivative depends on both the vectors and the point at which we are taking direction derivative. Is it clear?
Yes, sir. So the plane that you are showing that is passing through the point P and and it is
In the
it is in
direction
the
of the
direction
vector,
of U.
exactly. Correct.
Okay. So when I'm changing the point or when I'm changing the direction, the plane is itself changing. That's why the direction.
Exactly.
Okay.
Correct. Got it?
Yes, sir.
Great.
So how will you get the link for this, sir?
I will send you. Okay. I will send in the portal. So you have got the link of the earlier Geogebra, right? For the earlier sessions, I have posted in the announcement.
Where are you posted, sir?
Sorry,
Where are you
sir.
posted?
Yes, sir. We are
In the
announcements.
Portal announcement, I have sent earlier links also. Okay, somewhere there it is.
So can you, for a second, take it here, sir, straight away?
1 minute. Yeah, there, this announcement, okay, 15 March.
Okay.
Here you will get 3 links of Geogebra, which I have discussed in the earlier session.
Right, sir. Right.
So today's we'll add it up here later, sir, or today's link, that is this one which I saw, the one which
This one will I also post in like this announcement, okay?
Okay, under same this one, sir. Announcements.
No, a new announcement will come, no?
Okay. March 15th. Okay, thank you.
Yeah, okay. So this portion is clear, directional derivative. At least the visualization is clear, right? Anyone has any doubt in this visualization?
Sir, can you discuss the plane which you were showing?
A plane is basically for a visual representation which is passing through the point on which you are taking the direction derivative along the direction of the vector. Okay. That is for the visual representation only. Okay.
So then it is passing through P and it is in the direction. So the equation of the plane will be P plus T into U, right?
You have to find the equation of the plane.
Right, in the
So a
direction of
point
U.
is given and this vector is given. So you can find the equation of the plane basically. But you don't need it really.
No, I'm just asking for just for.
Yeah. Okay. Yeah. Okay, so this is done. Now let's see what this shows. Yeah, this is tangent plane and gradient vector. I think this is more or less clear to everyone. So one function I have taken, x square by 5, y square by 20. So it will look like this dome function. Okay. So at some point, so here I have taken some points. So let me fix it at 5,5. Okay. So this is the point 5,5. At this point 5,5, we are considering the tangent plane. So this is how tangent plane will look like. Right? Now, if we calculate the gradient vector at that point, okay, so you will see the gradient vector will be along this straight line, which is perpendicular to this tangent plane, right? That is the geometrical significance of the gradient vector. Okay, so gradient vector is basically the normal to the tangent plane. Okay, so if we move the points, we will get different tangent plane, and along with the gradient vector will also change. Okay, so
This
this is
part
how
is
Sir,
tangent plane
understood.
looks.
sir, I have a small doubt.
Yeah,
It means that gradient is always perpendicular to tangent line on a particular point.
tangent plane here, not tangent line.
I mean, yes.
So this is a surface, right? So here what we are talking about is the tangent plane, correct? At some point. At some point, if we talking about tangent, it is basically a tangent plane. And the gradient vector is basically perpendicular to the tangent plane. Yes, correct.
Yes.
Got it,
So
no?
tangent lines are like all the tangent lines are on that plane, right?
On that plane, exactly. Exactly.
Okay.
Exactly. Okay.
Yes, sir.
So yeah, this is quite easy thing to look at.
So which means a gradient vector along gradient vector only will have the maximum or the point of steepest ascent or descent will be on that perpendicular line, right?
I will come to that action and descent. I have a representation of that
Okay,
also.
okay.
Okay. I will come to that. So this here is another function x square plus y square equal to some y z equal to x square plus y square. This function. So at 1 comma 1, so this p point is your 1 comma 1. Yeah, this p point is your 1 comma 1. So if I first draw the tangent plane, so this is how the tangent plane will look like. So this is the equation of the tangent plane, right? This is how the tangent plane is looking like. Okay. Now if I want to see how the gradient vector look like, that is basically like this in this direction. Okay. So if I move the point now, you will see the tangent plane along with the gradient vector will move. Okay. Yeah.
So could you please show a visualization where the tangent planes are varying over the tangent plane?
Tangent planes are varying over tangent plane.
Tangent lines are varying over the tangent plane.
I mean, here itself, what you are seeing. Okay, let me stop. Yeah. So along this point, over this point, if we draw any line which is passing, which is on this plane and passing through that point, all this line will be tangent line, right?
Yes, sir.
So that is the thing. No? You draw any line passing through that point on this plane. There can be infinitely many lines,
Yes, sir.
correct? And all this line is basically your tangent line at that point.
So then it's true for all tangent lines that gradient is perpendicular to that.
Right. Because the gradient is basically perpendicular to the plane itself.
Okay,
Okay.
okay, sir.
Okay, great. Clear, no?
Yes, sir. So what is the normal line that you are drawing? What is that?
Normal line is basically the gradient vector. If we along the gradient vector, if we draw a line which is passing through that point, along the gradient vector, that is called normal line.
Okay.
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 Yeah. Okay, great. Now here you can change. So when I will send you this link, you can change your functions here. Okay, you can take different function here if you need. So xy, suppose this is your xy function. So for different function, you will get your visualization. You can play around with it. Okay. So suppose I want to take uh, x square plus xy. It will look like this, and at that point tangent will look like this. So you can play around with all this. Okay. So if I remove this tangent line, now this is the function how it look like. Okay. So this function, if we take this, I don't know whether it is work here or not. Yeah. This is the function xy by x square plus y square. See, at origin there is some issue with this function, right? We already know, because at origin this function is not continuous. Correct? So you can see at origin there is some issue from the different direction. We are getting some different limiting value. The function is behaving differently when we are approaching towards origin, right?
So is it possible to see that it is not continuous from this surface?
Directly you cannot see because this is a simulation which you are getting towards zero. But you can see the, I mean, if you zoom it, you can see how the behavior is changing, right? From different direction.
Yes, sir.
And that will give you an idea that this function is not continuous there. Because the limiting value does not matches actually. Okay.
Okay, sir.
So yeah, suppose we go to 0 comma 0. This is 0 comma 0. This is 0 comma 0 point we are taking. So yeah. And if we want to draw the tangent plane, it is not coming, right?
Yes, sir.
Because that function is not continuous there. So we really cannot draw a tangent plane at that point. Okay?
Okay, sir.
So I didn't
Yeah,
understand the discontinuity here. There is no discontinuity as per, like, we cannot see any discontinuity. Can we at 0, 0?
So 0, 0, you cannot directly show discontinuity here because this is a simulation. So I mean, whatever the closer, there is a value for the function, right? How close 0 will go. So you are seeing that
Okay.
thing, right? But if
See,
you take a close look here, so from different direction, the function is approaching with different values towards the origin, right? That
okay,
means the
okay, okay.
limiting value
Yes, sir.
at 0 is not fixed, right? The function is behaving
Yes.
differently for different values, right?
Yeah, see,
When we are
because
approaching towards 0, that
I
is.
wanted to ask you this because in 2D graph it's easy to show the discontinuity, right? Two discontinuity points. In 3D,
Not
how we
really,
can?
not always. Not
Yeah, not
always.
always. Yeah, not
Not
always.
always. Because in 2D graph even, suppose, okay, let me draw it.
Discontinuity is rather easy, I think. If multiple values
No,
are
not
presented,
always.
then no.
Not always. Maybe. Suppose what should I just take at which is not continuous at 0? Suppose for the function which is when x is greater than 0, function is y equal to x. Okay, when x is greater than 0. Okay, so from this point onward,
Yes, sir.
right?
Yes.
Okay, and at 0 we are defining it to be 0, so this is the origin. Okay, and
Okay.
for x less than 0, suppose I am taking x plus 1. Okay, so it is from here to here, the left side. Okay,
Okay.
now at 0 we know the value is 0, right?
Yes.
So here can we directly conclude
No.
from here how it is, I mean, what is the value, limiting value at 0?
No, sir. I understand.
I mean, whenever you're going near towards 0, I mean, this is not, suppose I am taking 1 by x, suppose.
Yes. Okay. Correct, sir.
Forget this function.
Yes.
Now, if I am asking what is the value at 0,
Yes, sir. Understand.
can you directly say it? No, right?
No, sir.
You have to zoom in and you have to go where it is going. It's never, I mean, as you can see, it is always going towards some point. It will, I mean, directly coming near y-axis, but it will never meet there, right? That is the point. So if you just zoom out everything, this is
I knew
how
a
it look like.
graph like this. It's called a direct function. It's a like a
That is
asymptote kind
yeah,
of a
that is
function.
also there.
Sir, like sine 1 by x also.
Sine 1 by x also, exactly. So you really don't can separate this from y-axis when you the value of x is coming near towards 0.
Yeah,
Correct?
this looks like impulse function. Correct,
Yeah,
sir.
but actually it does not matches with y-axis anywhere. It does not meet
Correct,
with
sir.
y-axis anywhere.
Correct, sir.
Okay, that is the point I was trying to. Yeah, so I hope this is clear, right?
Yes, sir.
And then the last thing which I want to discuss is basically gradient descent. So it's still loading here. Yeah. So here the function we are starting with, say x square minus y square. Okay. And some point is there. Here is the point which we are taking. And if we try to see the direction derivative here, yeah. Now this. Okay. So you cannot see. So you see the differential direction derivative value here, right? 1.53 now it is. Okay. Now what gradient descent says? Gradient descent says when it is along the direction of this gradient vector, then it is maximum, and when it is on the opposite direction of the gradient vector, then it is minimum, right? That is the gradient descent is saying. Correct? So
Yes.
if we change this vector, you see the direction derivative will change, correct? At some point it will reach maximum and it will become like that. So, okay. So let me fix some point here. What one should I take? 2, 1, let's say. 2, 1. Okay, so this is 2, 1. So this is basically what this look like on x and y xy plane. Okay, this left hand diagram, this is only on xy plane. So this is 2, 1 point p. Okay, and this is the angle, this is the direction of the vector which we are talking about, and the direction derivative is changing as you can see. Okay, so this is 4 comma minus 2. Correct? This is gradient. So if you calculate the gradient of this function at 2 comma 1, what we will get? This is 2x comma minus 2y. So if you put the value 2 comma 1, you will get 4 comma minus 2. Correct? So if I change this to 1, what the gradient vector will be? This is 2 comma minus 2. Correct? Is it okay? So
Yes.
can you tell me what is the angle of this angle it is making with x-axis? The gradient vector?
45 degree.
Is it?
Minus.
Huh.
Minus
45 degree. That means
Yes.
if we take it in the positive direction, 360 minus 45, right?
Yes, yes.
What does it mean? 315 degree, right?
315, yes.
So along 315 degree, it should be maximum. Let's see. See, this blue vector is your gradient vector. Now along that direction, I am taking my direction derivative. It is giving 2.83. This is the value. So what we have seen that this should be the maximum value. So let's change. Let's change the function. So if we go beyond that, the value will decrease, as we can see, right? Decrease from 2, so it come to 2 when I am coming to 360 degree. Again, if we are coming back, so at 315, it is taking 2.83, and then again it is coming back. I mean, it is decreasing 2.58, 2.48, and again it is decreasing, right? And now it is coming as minus. So the maximum value is indeed 2.83 of the directional derivative, and it is coming at 315 degree.
How did we get minus 45 degree?
This is sine, and this is cos. So tan theta is basically -1, and it is in which coordinate it is? Here,
Okay, sir, got it.
sine is negative, cos is positive, right? So it should be in fourth quadrant, right?
Yes,
and
sir.
tan theta is -1. So what is the value? 350.
So you have taken that is tan of minus theta, right?
Right. Okay, no? Is it clear? So you can see at 315 the value is maximum. This is 2.83, and if we move from 315 the value will come down. Okay, so this is the definitely the maximum directional derivative. Okay, and what is the opposite direction of that? And where it is the lowest? What should the
135,
degree?
135 degree, 135.
135, exactly, 135. So let me put 135 and see what it look like. This is -2. Is it okay? And that is basically the norm of this gradient vector. You can see this is the norm, right? Okay, so whatever theory you have done there, it is the visual proof of that. Is it okay? Is it clear?
Yes, sir.
How you got this 135, sir? 135 degrees, how did you get that, sir?
So opposite of basically the earlier vector, that is negative of this gradient vector, -2, 2. Okay, now sine is 2, cos is -2, so tan is basically -1, but now sine is positive, cos is negative, so it is in second quadrant, right? Now second quadrant means where sine is positive and cos is negative, so it is 135 degree between 90 and
okay.
180.
You know, measuring on from the anti-clockwise system.
Exactly. Okay, so the value should be exactly minus of 2.13. I mean, the 2.83 is maximum and -2.83 is the minimum. So is it clear? So you can see this is the direction. Yeah, this is the direction derivative, the straight line which we are talking about, the slope which we are calculating. So this is how it looks like. Okay, if we change this direction, we will get different values, which is lying between -2.83 to +2.83.
So you are doing
Okay.
this in GeoGebra?
Yeah.
Okay.
Okay. So here also you can change your function and you can play around with different function and different point, different direction derivative you will get. So you can check whether whatever you have done in problems, you can see it here. Okay.
So basically, in the direction of gradient vector, it will be fastest, and in the just opposite direction, it will be minimum change, right?
Minimum, exactly. That is what we have learned, right?
Yes.
In the first lecture of week 10.
Yes, I think.
Yeah. Okay. So hopefully this 4 will help you, this 4 representation. Okay. So I will send all this 4 to your announcement and you can check it from there. Also, I will give it in discourse also, you can get it from there also, okay?
Thank you.
Yeah.
So is this GeoGebra self-explanatory, or will you get a tutorial on this, how to use this GeoGebra?
No, these are basically applets which is already made. Okay, so you have to just put your function, you have to put your points, you will get that.
Okay.
All these
So
are inbuilt here. Now, if you want to make your own applet, then you have to know what programming is going beyond that.
Okay.
That in the earlier session, I have discussed some of that.
Okay.
Okay. So yeah, so I have nothing more to say in this week because week 11 there is very less content anyway. And from next day onwards, I think we are going starting with the revision session for exam.
Yes, sir, as per calendar.
Yeah. So from next day we will start with the revision session.
Sir, are we going to study maths in diploma courses also, sir?
No, if you have completed your maths 1 and maths 2, then
No, no,
it's
no.
all.
Any new maths content. I'm saying new maths content.
No, no, no.
I
Not
think in
really.
machine learning we have to learn math.
That is machine learning course, and here you will see all this again.
So
Not
this
again, mean
content
not
will
totally. I mean, you have to use all this there.
so all this content will be available na, when we go to that
Diploma
if you
course.
want to revise
Yeah,
this
yeah, for your, yeah.
So, like on dashboard we have been given a book on vector calculus. So, are we going to study that in down the line in new courses?
Yeah, vector calculus will be. I mean, whatever vector calculus you will require, that will be in machine learning course.
In machine learning.
Yeah. So machine learning in linear algebra will starting with eigenvalues and eigenvector. All this will come.
That machine learning foundation. There is a course called
Yeah,
machine
machine learning
learning
foundation.
foundation.
Exactly. Machine learning foundation.
Sir,
And then you have to use this multivariable critical
calculus
points. All this
again.
will come again.
Correct.
Yeah.
Sir, as just now we were discussing that derivative, whether it's for one variable or multiple variable, it is basically rate of change, right?
Yeah.
And it's a number, right?
Hmm.
So the essence remains the same. So I'm
Hmm.
just trying to understand, sir, through a word problem. Let us say that the selling price of a product is 4 times the cost price of the product, right?
Okay.
So we can write that y equal to 4x, right?
Yeah. Okay.
So if we differentiate it, so we get dy by dx equal to 4. So it means for 1 unit change in cost price, my selling price will go up by 4 times, right?
Exactly. Exactly.
But say for example, if the function is defined, if the now the relation is defined like this, y equal to x cube minus x square. Now my selling price is a function like this, x cube minus x square. So my
Okay.
first derivative will be 3x square minus 2x, right?
Right.
Then how to decode this, sir? How to decode this?
Now, depending on this x, now x, what is your x? X is your
Variable. Sorry,
it
cost
is a
price,
variable,
cost
but
price, cost
cost
price,
price. Now,
cost price,
so
right?
suppose your cost price is 100. You
Okay,
know what is your selling price at that point, right? What is the rate of change of selling price at that point? That
okay. So,
is basically the derivative gives you.
so we'll have to plug that value, right?
Exactly.
Okay.
So that
And
is what I am saying. If you are not mentioning a particular point, then it will come out as a function of x, function of the
okay.
variable you are starting with. Okay.
And when we maintain a value, so similarly we have to plug that value in dy by
Yeah,
dx.
I mean that is here. So same thing is happening. No, suppose I have fxy. Suppose x square plus y square. Okay, this is a function of two variable.
Right.
Okay. Now suppose along the direction of x-axis, what is the change? So what are you want? What do you want? Basically, you want the partial derivative with respect to x, one variable, right?
Okay.
So this is 2x. So this is a function of x alone, right?
Right.
There may be y also, but in this case, it is function of x alone, right? So for defined values of x and y, you will get defined values of this change, right?
So let us take that one variable example, sir. Y equal to x2 minus x square. Y equal to
Uh,
x2 minus x square. So this is my selling price and x is my cost price. So now
uh,
if I differentiate, so dy by dx is 3x square minus 2x, right?
this is a function on x, yeah.
Okay, so say for example, now if I say that my cost price is going up by 2 rupees, right? So
Uh,
it means that now I have to put the value of x as 2.
right.
Okay,
So we'll get value of dy dx. What is the change at that point? So what
perfect.
does this mean? So if you remember your one variable
Correct.
calculus,
So that physical interpretation is very important.
so if you know this one variable, suppose say forget all this, just take y equal to x square. Okay?
Yes, yes.
This is a parabola, right?
Yes, sir.
So rate of change at this point and rate of change of this point are different here, right? Here the rate grows, right? So y equal to x square means what? Dy dx is 2x, right? So rate of change is 2x. I mean rate of change is linear, right? So when x equal to suppose 1, your rate of change is 2. So if you draw a straight line here, this is 2. Now if you draw a straight line here at this point, what is this? Suppose x equal to 5, this is,
So
or
that is
3.
10.
That is, suppose
Okay.
3. Then this is 6.
6.
Okay, so this and these are not same.
Yes. So
The
this
rate at this point, rate of change of this function at this point is not same as the rate of change of the function at the previous point. So it is a depend on x, it depends on the points.
Correct. And so the other way of saying this is that the value of slope is 6, right?
Exactly. The
Okay,
increment
and
is 6,
that is
no
also
value. I mean.
And that is also tan theta.
If this is theta, then tan theta is 6 basically.
Tan theta is 6. Yeah. And so when we differentiate a function, so whatever resultant we get, like here we got 3x square minus 2x, right? So it is again a function, right?
Yeah, here also y equal to x square, here also it is again a function, right?
Okay.
2x.
Okay. So again, say for example, again if I have to differentiate, so do we need to go back and again check a value of limit and continuity before differentiating?
See, I mean, what is your confusion now? I am not getting. Basically, you are repeating the same thing
There
now.
is no confusion, sir. I'm just trying to understand in the simplest manner. So like
So basically, what differentiation does, what
right.
derivative does, derivative is giving you the rate of change of the function at that particular point. And the rate of change of the function may be dependent on some other variables. Okay? It may not be constant always. It is constant only for a straight line.
Okay. That was my question, sir. Like we got f dash first time derivative, we got 3x square minus 2x, right? So this itself is a function.
Exactly. That's what I have said.
So now if I have to differentiate it further, so do I need to evaluate the limit and continuity again?
I mean, as a definition, it is always the same. But when you are doing differentiation, are you checking the limit and continuity of x cube minus x square?
No.
No, right? Because these are polynomials. This is always continuous. So you don't have to really do that.
No, here it is polynomial, it is understood.
But if there is some such a situation where there is a chance, there is a possibility of being not differentiable or not continuity, then you have to check it for at every place. You have to check it. Whenever you are doing some differentiation, you have to check first that whether the function is differentiable or not.
Okay.
Okay.
So second order derivative is again the rate of change for first order derivative.
Exactly.
Okay.
So just take an example of just a particle in a physics. We have to.
I am not doing physics here. I will not take that example. Okay.
Sir, I have.
Yeah.
No, sir. I was telling him that if we take a example of physics for first order derivative or a function in distance, we have to derivate dx over dt gives us a velocity.
Speed, right? And second order is acceleration.
That she knows.
That's what you are trying to say, right?
Yeah. Basically, it is a rate of change of a function. Now, if the first order derivative is itself a function, then it is rate of change of the first order derivative. That is your second order derivative. The third order derivative is rate of change of your second order derivative.
Till the time we get a constant. Till the time we get a constant.
Yeah, if you want to look at like this. Then okay.
No, that's not necessary to get a.
I mean, there may be a point that it never becomes a constant. Why it always should be a constant at the end? Okay. If it is a polynomial of some finite order, then obviously at some point it will become a constant. That is okay. But there are some functions that it is possible that it may not be constant.
Sir, can you mute?
Yeah. Okay.
Yes, sir. Yes, got it.
Okay. Okay. So
Sir, if
yeah,
no one is asking questions, then I have a doubt, sir.
yeah. Go
Yeah,
ahead.
this is related to what you responded on discourse also related to vector only, sir.
Mm-hmm.
So somewhere I'm cutting a sorry figure that I'm still not able to comprehend that how come there is no existence of vector in isolation. Like as someone was quoting about velocity and acceleration. So in our school days, for the first time, we come across a vector and differentiation while studying velocity and all, right? So there we simply say that it's a vector having magnitude and direction. But while in this course we are studying that there is no concept of vector living in isolation. It is all about vector space. So somewhere still
Yeah.
I'm not
So
able to
here in
comprehend.
this course,
I'm not able to comprehend this point, sir.
here in this course, what we are doing here in this course, we are treating vector as a point of a space, as a point of a set, right?
Right.
As an element of a set which has some properties, right? Suppose in case of R2, if you take in R2, what you are getting?
There will be two coordinates. There will be a point having two coordinates.
Huh. So if you take any point, suppose this is your vector 1, comma 2.
Right.
Okay. Now, in school days, what you have seen this is your vector, which
Right.
is the line joining 0, 0 and 1, comma 2. That is your vector in school days you have seen. It has a direction. Definitely it has a direction.
Correct.
Right? And this is your increment, right? Inclination of the vector with x-axis, right? So, yeah, these two are related, but here we are doing it in more general thing. Not only the magnitude and the values, magnitude and the direction. We also know magnitude and the direction because we have seen inner product space, right?
Correct. Correct.
So where basically we are dealing with norms and inner product.
Correct.
That is basically your magnitude and direction. Okay, but here we are doing it more general way.
That
Okay,
is the reason why the concept of vector space is coming into play.
exactly.
And those 10
And
axioms are there,
the
right?
point is only this point on R2, R3. These are not only the vector spaces. Okay, there are many other spaces also. So matrix forms a vector space. Set of all matrices.
Even sir, yes sir, correct. While
So there are
exploring, I also
many
came to know
things
that it's
coming into
not
the
only
picture.
about vector, even it can be a function also.
Yeah, it can be a function also. The points on the vector spaces can be a functions also. That is called
Because we are
function
taking
space.
because we are taking two different sets. One from V, one belongs to V, and the other belongs to. Hello, sir, am I audible?
Yeah.
And the other belongs to F field, right? So it can be a
Yeah.
function also, right?
Function of what?
Like we are taking na
Which can be a function.
in V. An element can be a function also in V. That's what I'm trying to say.
Yeah, right.
Right.
But we don't need it for this course. Okay?
I know.
Yeah. But that can be function also. Yeah.
So it's
The
a
operation may be different. That is
correct.
also yeah.
So it's a general approach. That's what we are saying, that it's a vector space.
Exactly.
And sir, in this while equating to find the critical point, we are getting many equations. Sometimes we are getting in terms of x square equal to something, right? Say for example, x square equal to 9. Then we are taking the value of x equal to plus minus 3, right? It might be very trivial, sir. This point was discussed earlier also with Subhasis, sir. I think along with me, there were a couple of more people who could not understand the concept. When we are saying x square equal to 9, then we are saying x equal to plus minus 3. But when we are taking the square root of 9, then the outcome we are saying, it is only plus 3. We are not considering
because square root of some number, that is a particular number. There is a difference between x square equal to 3,
9,
x
yes.
equal to suppose 3 and x equal to root 3. There are difference between these two. Right?
Why? Because complex number is getting into picture. That's the difference, or what?
No, where complex number is coming here.
So say for example, we say that plus minus 3. So
Where complex number is coming. Plus minus 3 both are real number, right?
Yes, those are real numbers.
So here we have two solutions. One is x equal to plus root 3 and x equal to minus root 3. This
Right.
minus root 3 is a symbol of a number. What are these 1, 2, 3? These are all symbols, right?
Right.
By which we understand some number. Similarly, root 3 is also a number. This is on real life. This is 0, 1, 2. Here is somewhere is root 3.
Correct.
And
Yes.
here it is minus root 3 somewhere.
Yes.
So when we are saying just root 3, this is a positive number.
Right.
Minus root 3 is a negative number.
Yes.
Got it?
Yes. So that's about square, square. But when we say square root of 9,
instead of 9, I am talking about 3. So, okay, square root of 9. So
Okay.
there somewhere it is square root of 9, it is 3.
3 and
This
minus
is
3
minus
also.
3. And these are basically, this is basically square root of 9. Just another representation of it.
Right.
Here it is minus square root of 9. But square root of 9 is a positive number. Got it? Got it, no?
Yes, I got it this point, sir. I think I was not able to explain the question. I'm saying that the discussion was like this. When x square equal to 16, right? Then we are saying x equal to plus minus 4. But when we are taking square root of 16, so on that day somewhere there was a mix-up that we can take only plus 4, not minus 4. That was the confusion, coming out on that day.
That is what I am saying, that square root of 16, this is a positive number.
Yes,
this has nothing to do with x square equal to 16. This is the one solution for x square equal to 16. There are two solutions. One is plus root 16, another is minus root 16. Okay?
Okay.
And this is basically, this is plus 4 and this is minus 4. Okay? Got it?
Okay. Yes, sir. Got it.
Yeah.
Thank you, sir.
Yeah. Okay.
Sir, I have a doubt. Actually, I could not get the point. Why gradient vector is normal to tangent plane when?
Why gradient vector is not? No. Gradient
Normal.
Vector is basically the vector which is normal to the tangent plane. That's how it is defined. I mean.
Actually, it is definition or some mathematical proof is there.
No. I mean, we cannot prove whether gradient vector is a normal. I mean, normal to the tangent plane. I mean, if we want to find the equation of the tangent plane, so we have to find the slope of the tangent plane, right?
Yes, sir.
And by finding the tangent plane, we see that we are need some vector. To find the slope of that, we should be perpendicular to the tangent plane, and that vector we name as gradient vector.
Okay. Actually, gradient vector is the all the partial derivatives.
Exactly.
And it is a.
Hello. Hello. Am I audible?
Yes, sir. You are audible. She is there.
Excuse me, sir.
Yeah.
Sir, that GeoGebra question, can you open that?
Which question?
That,
yes, sir. Hello, sir. Hello.
Yeah, Anamika.
Yeah. Is it? It is a fact that at any point gradient vector is always normal to tangent plane. Is it?
I mean, that vector we call it gradient vector, which is normal to the tangent plane. That vector we call it as gradient vector.
Okay. Any normal vector to the tangent plane at some point.
Not any normal vector. There is only one at that point.
Yeah,
that
only.
Is the gradient vector.
Okay, sir. Okay.
Yeah.
Sir, can you open that GeoGebra question that we were discussing?
Which question?
Yes, sir. Yes, this sir.
This one?
Yeah. Sir,
okay.
In this in inner product space, you have written 2 minus 2. Okay, sir.
That is not inner product space. I mean, that is written here like that, but that is basically point 2, the vector.
Sir. And you have told that this is these are value of sine and cos.
To understand it, I mean, where the direction of the vector is. So how we'll find the direction of the vector? What angle it is making with x-axis?
Okay. So that, sir, these are not the value of sine cos, because I was confused that the value of sine and cos
No,
fluctuates between 1.
basically how we are finding this theta. Theta is basically the angle which is making, I mean, the vector is making with the x-axis, right?
Yes, sir, yes,
Theta is that angle. So for
yes,
that
sir.
we have to take it to polar coordinate basically. So I did not want to go there. That's why I am just saying take the first one as cos theta, second one as sin theta, and do it. You will get the same thing. But what is the logic behind it? I am not going there. Okay.
Okay,
Because
sir.
we
Okay,
have to
sir.
transfer it to the polar coordinate. Then we have to find it. Okay. The first one is r
Yes,
cos theta. Second one is r sin theta.
yes,
R
sir,
is
yes, sir.
basically the norm of the vector, right?
Yes, sir, yes, sir.
So
Yes, sir.
basically by the end you are getting that thing associated with sin theta, the right hand side, and the left hand side associated with cos theta. So
Okay,
basically
sir.
you will get some tan of theta.
Yes, sir, yes.
Okay, there
Yes,
is
sir.
no issue with
Uh,
that.
Sir, polar that was discussed in
Polar coordinate is not in our
11th class,
syllabus.
11th class complex numbers.
Yeah, right. There you have learned that exactly.
Yeah, okay, sir.
Okay.
Thank you, sir.
Anyway, you will get minus 2 by 2. That is your tan theta in that
Yes,
sense,
yes, yes.
right? From there we are basically getting it. Yeah. Yeah. Okay, so I am stopping this session now. Uh, Hope more or less till week 11 all the concepts are clear. We will get back to the revision session next. Okay? Okay, so hopefully you will start preparing for the answer. And how was your quiz 2 result? More or less it is fine, right?
Yes.
It is what you expected or more than that?
I have
And the
expected less.
questions?
I scored more, sir.
Okay, great. So quiz 2 was easy, right? Okay, great. So prepare well for the end term, okay?
Sir, will
Because
there some
you,
revision session for NTM?
there are 4 revision sessions for end term.
Okay.
Okay. You prepare well for the end term, okay? Because quiz 2 was really easy, I think, for all
Yes.
of you. So yeah, hopefully we'll see. Okay, bye.
Thank you, sir.
Yeah.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you, sir.